So today we're going to talk about the beautiful construction of the 17 gon. You might feel a bit confused because didn't we already just talk about constructibility of the n-gon? Isn't the 17 gon only a special case of the n-gon? Well, yes, but no, technically these are two different stories. Gauss actually constructed the 17 gon when he was just 19. It was not until 5 years later that he found the sufficient and necessary condition for the constructibility of any regular n-gon. Thus his proof that the 17 gon was constructible was actually done by explicit construction. And it involves some really deep ideas. Actually, when I was in Russia, I once went to this amazing talk where the speaker explained how Gauss could have come up with one of his crowning achievement, quadratic reciprocity. He showed how many of his ideas could have come from this period when he was working on the constructibility of the 17 gon. So let's look at the proof and see if you could recognize any of those ideas. So let's construct the 17 gon. Recall that by our previous discussion, this means that we should look at the field Q adjoining the 17th primitive root of unity, i.e. the 17th cyclotomic field, and then a construction of the 17 gon, which just correspond to a chain of subfields, such that the degree of the extension involving any two consecutive fields must be 2. Recall that this is because the coordinates of the points constructed via straight edge and compass can be obtained by solving equation of degree less than or equal to 2. Okay, so constructing the 17 gon mean obtaining a sequence of subfields like this. Now, from the proof of the constructibility of the n-gon, we know that a way to obtain this chain is by looking at a chain for the corresponding Galois group. Previously, we have seen that such a chain exists for the n cyclotomic field if n is the product of power of 2 with Fermat primes, i.e. primes of the form 2 to the 2 to the m plus 1. This works, for example, if n is say 5 or 17 and so on. Thus, n equals to 17 is the first constructible n-gon that people didn't know about. So, we know for sure that for 17, we will have the following chain of subgroups, where the index of gi plus 1 inside gi is going to be equal to 2. And then using Galois correspondence, in particular taking this ki to be the fixed field of gi, we will get a chain of subfield. Well, that shows the constructibility of the 17 gon. But that's not what we want. What we want is the actual construction. So we want to find these fields here explicitly. And for that, we need to find these groups explicitly. So let's do that. So, what is the Galois group of a cyclotomic field? Observe that every element in this Galois group is uniquely determined by where it sends this nth root of unity. The image must be a root of the same minimal polynomial, so it must be another primitive root of unity. Thus, it must be zeta n to some power a, where a and n are relatively prime. We can call this map sigma a. Then we see that this Galois group is just the unit group of z mod n z, where the correspondence is that sigma a should correspond to a. Now, it's very easy to find a chain of subgroup for this, because this is just a cyclic group. And so, it has a subgroup of every order dividing this order. So we can start by finding a decomposition here that gives a decomposition of the Galois group, which then, by taking fixed field, gives this decomposition of the cyclotomic field. The subtle point will be, once we have a subgroup here, how do we construct a fixed field up here? And that's where the interesting stuff about Gaussian periods come in. So stay tuned. Let us first illustrate this idea by trying to construct the pentagon. Here n is equal to 5, and the Galois group is just going to be isomorphic to z mod 4z. Being a cyclic group of order 4, it should have exactly one subgroup of order 2 and one subgroup of order 1. In z mod 5z star, this is just a subgroup generated by 1, 4. In the Galois group, this should correspond to the subgroup generated by sigma 1 and sigma 4. Where remember, sigma a was defined to be the map sending the primitive fifth root of unity to its 8th power. Now, to get the chain of subfield, we need to find the fixed field of this. The question is, what is this fixed field? And this is where Gaussian periods come in. For each of the subgroup here, we're going to construct something called its period. And it will turn out that that period is going to generate this fixed field. So let's see what the period should be in this case, and then see if you can generalize the idea. Alright, so to find this period, which generate the fixed field of this g1, I should at least make sure that it itself is fixed by this g1. Now, what's the easiest way to get an element that is fixed by G1? Well, we can just sum up the orbit of zeta under this subgroup. In general, given a subgroup H of the Galois group of this n cyclotomic field, we can just define the period corresponding to H to be the sum of elements in the orbit of this primitive nth root of unity under H. We can see immediately that H must fix its period. Why is that? Well, if we take some tau in H and then apply tau to alpha, we'll see that tau is just gonna permute the term of this sum, so we get the same sum. This is because as sigma ranges over element of H, tau sigma also is just gonna range over element of H. Thus, every element of H fixes alpha. So alpha must lie in the fixed field of H. That is, Q alpha H is going to be a subfield of this fixed field of H. But we claim that they should actually be equal though. That is, alpha H should actually generate this whole fixed field. So how do we show this? Here again, we want to use Galois correspondence. We just need to show that the subgroup of the Galois group that fixes this extension is actually just H. Alright, so let's do that. Let's say tau is an element of the Galois group that fixes alpha. This means tau alpha is just equal to alpha. Now we claim that this means that these terms here are just gonna be permutation of these terms here. Why is that? Well, because this being images of zeta n under field embedding must be primitive roots of unity. And the primitives and roots of unity form a basis of this cyclotomic field over Q. So in particular, if these two sum are equal, then that equality must be term by term. Each term here must be equal to some term in here. In particular identity times zeta n is a term up here, so it must equal tau sigma zeta n for some sigma here. And now because elements of the Galois group are uniquely determined by what they do to this zeta n, we actually have that these two maps must be equal. In particular, tau must be equal to sigma inverse. But sigma was assumed to be in H. So this means that tau itself must be in H. And thus H contains all the elements that fixes alpha. On the other hand, we already knew that H fixes alpha. So then we actually have an equality. Now by Galois correspondence, this means that the fixed field of H is just generated by this Gaussian period. And now back to the discussion of the pentagon, we know how to fill in this subfield here. By definition of the period, it's just gonna be the sum of the orbit of this zeta under this subgroup. And then by definition of the sigma I, that is just gonna be zeta 1 plus zeta to the 4. And that is how we can give an explicit sequence of subfield of this fifth cyclotomic field that would correspond to a so-called construction of the pentagon. This idea works for constructing a regular n-gon in general. If we know that an n-gon is constructible, then we know that we have the following sequence. That is, a chain of subgroups of the Galois group of the n cyclotomic field, such that these relative indices are 2. We can always construct this explicitly by using this identification of the Galois group with the units of z mod nz. We first decompose this group, then we find the corresponding subgroup in the Galois group by replacing every element A in here with the automorphism sigma A. We then use Galois correspondence to get a chain of subfield by taking the fixed field of these. And explicitly, the fixed field of GI is just Q adjoining the period corresponding to GI, where this period is just going to be given by the sum of all elements in the orbit of this primitive root of unity under GI. In particular, if GI corresponds to this subgroup A1.AR of this Z mod NZ star, then this period is just gonna be given by zeta to the A1 plus zeta to the AR. So that's how we can explicitly find this chain of subfield if we know an n-gon is constructible. Now there's some exciting news. Actually, we can be even more explicit than this. In the next video, we're gonna discuss how to compute these periods out explicitly in terms of radical of rational numbers. As a corollary, for every constructible n-gon, we will be able to compute cosine of 2 pi over n in terms of radical of rational numbers. For example, from the constructibility of the 17 gon, Gauss got this expression. So that's what we're gonna cover in the next video.